Perhaps you can take your seats. It's 9 o'clock and I think we should be starting on time. I hope people online can see and hear us. Okay, it works. Apparently, that's very good. This is a hybrid physical and online meeting, and I think these are the most difficult ones nowadays. I am sharing my screen with today's agenda. This is going to be a two-in-one workshop. First, the first part will be an overview of the three anion exchange membrane electrolyzer projects that we have supported from the 2019 call for proposals. ANIONE, Chanel, and NEWELY will be presenting their findings and challenges. And then this will be followed by a presentation by the JRC on the harmonized testing protocols for accelerated stress testing. Following a lunch break, we will have a roundtable discussion on electrolyzer degradation. Each speaker will take around 15 minutes. I appreciate that in the morning session, we will not have the presentation from ENAPTER, but please let us know if someone has joined remotely and will be giving this presentation. That means the first set of presentations can be perhaps a few minutes longer. I will be sharing the presentation material on this laptop, so I'll be inviting every speaker to come and sit next to me to use this laptop and the microphones. We can use 3 of these microphones at the same time. If someone else wants to speak, we'll have to mute one of the 3. And with this, I think we can start with a presentation of mine. I can get to the right folder. It's this one. Right. So, brief overview of the support the Clean Hydrogen JU has given to electrolysis technologies. I'm focusing actually on low temperature, mostly here. Briefly, the Clean Hydrogen Joint Undertaking is a public-private partnership between the European Union, representative of the European Commission, and European industry and European researchers. For this framework program, we have a budget of 1.2 billion euro over this 7-year period. Our strategic research and innovation agenda covers the full value chain from production, distribution and storage, end use, and then horizontal activities. Production, distribution, and storage, you could say research in these fields is a kind of monopoly for our JU. When it comes to end use, this is an area of synergies and collaborations with many other agencies or JUs that have now stepped in to support demonstration in these hydrogen-related technologies. And then horizontal activities goes from cross-cutting to hydrogen valleys, strategic research challenges, etc. Clearly, this workshop is dealing with the left top part, the electrolysis. The legacy from the FCH-JU days is that we have till now, the last 15 years, supported 337 projects for 1.4 billion euro. You can see the distribution per area. Hydrogen production has become more prominent, let's say, recently, has enjoyed 18% of this support. And in terms of electrolyzers, you can see on the left-hand side that PEM electrolyzers and solid oxide electrolyzers have enjoyed a lot of support, less so for alkaline since this was considered a more mature technology. And on the right-hand side, you can see how this support changed over the years, with 2 gap years where the framework programs change and we couldn't have a call for proposals. You can see 2022, we had 2 calls. Basically, it's for covering 2 years, but still an impressive increase, covering alkaline, PEM, solid oxide, and anion exchange membrane electrolyzers, the little red bars. Also very important is that funding went almost equally, a third to SMEs, almost a third to universities and research institutions, and a third to industry. 20 years ago, when people were discussing a joint undertaking, there was concern that industry will be taking all the funding, but we can see that things went quite well. And on the left-hand side, and on the right-hand side, same picture, but showing the number of beneficiaries. And we can relate that once you have RIAs, research innovation actions, there is an increased number of beneficiaries involved compared to years where we had mostly demonstration projects or EAs. So briefly, the large electrolyzer demonstration projects that you can see here, you can see capacities going from 150 kilowatt all the way to 20 megawatt and 30 megawatt of the recent large demonstrations. Capacity increased by 500 times, and the funding that we have been providing per installed megawatt reducing by 100 times. That shows economies of scale, but also increased commitment from the participating companies. So PEM projects in blue, red projects are the alkaline. Most recent projects, Jules, that is also feeding a valley called Heaven, and Ephira, that will feed a valley called Tri-Iris. These large demos allow the creation of an interesting feedback loop between the electrolyzer OEMs and large industries that helped establish a solid basis on which we think the EU hydrogen strategy was also built. On the right-hand side, you can see some bullets of 2 projects. H2 Future achieved an efficiency of 83% high heating value. Hydrogen was used in a steel plant. The operating range was an impressive 15 to 150% of the nominal capacity, and hydrogen production costs could be reduced by 25 to 50% through the provision of electricity grid balancing services. Project Refine is still up and running, identified various issues related to finding suitable balance of plant, and this will apparently be coming into play in our future calls, the balance of plant. And after the war in Ukraine, the increased cost of electricity, of course, didn't help their testing campaign, this 10 megawatt electrolyzer. 2018 call, 2 projects on game changer low temp electrolyzers going to very high pressures and current densities. A number of challenges that were faced by these 2 projects. So this issue has reappeared on our calls for proposals. 2019, we'll be hearing about the 3 projects that have been running in parallel and have set a positive precedent in terms of collaboration between these projects, as we will hear. Just to inform you at the bottom, 2022 call, we have supported 2 anion exchange membrane electrolyzer new projects, Heracles and High Scale, and we're going from the 2 kilowatt testing electrolyzers of the 3 projects to 25 kilowatt and 100 kilowatt, and from 100 square centimeters to 400 and 500 square centimeters, quite high pressures as well. We are also going offshore. Project Oyster from 2020 is actually a near-shore facility with a 3 megawatt alkaline electrolyzer that will be installed in Zeeland. And 2022 called Project Hope is a 10 megawatt PEM electrolyzer that will be going 1 kilometer offshore on a recycled barge. It started recently. Same call 2022 in terms of research projects. We have 3 new projects: Advanced PEM, that's looking at hydrogen production at 200 bar, validation at 50 kilowatt. IPRAEL is an alkaline electrolyzer, same as PEACE. So we are now funneling support to alkaline electrolyzers as well. And you can see high pressures of operation being targeted and demonstration at 50 kilowatt. Same call, Project EFIRA that I mentioned previously, a 30 megawatt electrolyzer where the hydrogen, the oxygen, and the waste heat of the electrolyzer will be used in a refinery location. So it's a kind of industrial symbiosis. And also very important is the digital twin, the control strategy, control system that is going to be implemented. And yes, I think this is my slide. I thought I had one more. Let me see if I can. Indeed, it's this one. Maybe I can share again. Oh no. Very happy to move to the next slide. But I was hoping just to share that we had in our recent call for proposals topics on innovative electrolyzers, and we received a record 24 proposals of very good quality, showing an impressive European community active in research in these fields. And now we're talking really innovative, very low TRL stuff, membraneless electrolyzers, capillary fed electrolyzers, etc. This was impressive, and we hope to be able to support perhaps more than one proposal. And again, a topic 1.3 on, again, alkaline electrolyzers, where 7 proposals were received. And with this, I conclude my overview of our support to low temperature electrolyzers. And I will then move on to invite Professor Antonino Aricò, who was a key person in organizing this event, to give his presentation. Let's hope things are going to work, and I hope people at home or in the office can hear us. I think I need to press now F11 to make this full screen. And Professor Aricò, the floor is yours.
Thank you so much, Nikos, for your kind introduction. My name is Antonino Aricò. I work at the Italian National Council of Research. I had the honor to coordinate the ANIONE project that was dealing with anion exchange membrane electrolysis for renewable hydrogen production on a wide scale. Just a few words about the partners involved in the project. The project, as mentioned, is coordinated by CNR, ITA, that is the Italian National Council of Research, the Institute of Advanced Energy Technologies in Messina, Sicily, and we have as partners in this project CNRS from Montpellier, France, involved in membrane development, especially reinforced membranes, and Hydrolyte from Caesarea, Israel, that is working on the development of the polymer electrolyte, anion exchange membrane, polymer electrolyte for this application. And the previous name was PureCell Tech. and TFP from UK that is involved in scaling up of electrocatalysts, IRD from Denmark that was dealing with MEA fabrication, and Cummins Accelera by CUMMINS-HYDROGENICS that has also supported us in organizing this event, and they are involved in stack development. And we have also Uni Research. Uni Research is especially involved in dissemination and exploitation activities, and strongly collaborating also with the other AEM electrolysis projects, Chanel and NEWELY, and also assisting the project coordinator in project management. So, I think it's moving slowly, no problem. Full screen, possibly?
This is full screen.
Okay, it doesn't matter. It doesn't matter. Okay. So regarding the project objectives, the aim of ANIONE was to develop a cost-effective and durable AEM electrolysis technology, but also characterized by good performance. That means low energy consumption, low degradation rate, and reasonable capex. And to achieve these challenging targets, we tried to develop advanced materials in terms of membranes, electrocatalysts, especially focusing on non-critical raw materials. And all these innovations have been validated in a 2 kilowatt AEM electrolyzer with a production capacity of about 0.4 normal cubic meter of hydrogen per hour. That is about 1 kilogram hydrogen per day. Of course, in the project, our materials and systems have been designed to operate with diluted KOH, not with pure water. We think that this is a good trade-off between, let's say, not impacting so much on the balance of plant, but still maintaining a good performance and especially good efficiency. And just let me move to the second slide, but I have some difficulty. Page down. Let me see it. Okay, thank you. Thank you so much. So how you eventually can okay with the mouse. Okay, with the mouse. Okay.
Finger.
Okay, good. So regarding the ANIONE project, we started at technology readiness level 2, and during the project we achieved the technology readiness level 4. We started developing reinforced membranes, electrocatalysts, and all these materials have been validated in the stack. And regarding the membrane, I will say that the membrane is the key material, the key component in this technology. And at the beginning, when the project started, we identified the 3 main routes for membrane development. The first route was essentially based on perfluorinated membranes with ammonium, quaternary ammonium functional groups. That is an analogous of Nephion, just to achieve good durability for this system. But we moved easily to hydrocarbon membranes developed by hydrolyte, polyarylene, and or polyolefin-based membranes, still based on quaternary ammonium functional groups, and also the DAPCO was developed, and these results have been published in the papers you can see indicated in the slide. And now, regarding the membrane properties, starting from the hydrolyte membranes, these membranes are characterized by good thermal stability, as you can see from the TGA, and especially good chemical stability. That is very important when you operate with diluted KOH. These membranes are essentially not losing significantly functional groups when they are immersed in a concentrated KOH, while benchmark membrane is instead showing a lower stability. And now, one key development of the project was regarding reinforced composite membranes. Why reinforced membranes? Because we need good mechanical stability, good dimensional stability, and especially also this should be characterized by good conductivity, ion conductivity. In particular, with these reinforced membranes, we got a conductivity of 100 millisiemens per centimeter. And of course, this membrane was also characterized by good mechanical resistance. Now, coming to the electrocatalyst development, in ANIONE we have evaluated, assessed the different electrocatalysts, especially based on non-critical raw materials. And we have essentially focused our attention on the combination of nickel molybdenum on carbon at the cathode and the nickel iron oxide at the anode. Indeed, this is a nickel iron layered double hydroxide, and this was the best combination, showing the highest performance comparable to what can be achieved with let's say, precious metal electrocatalysts. What is really important is also understanding the Faraday efficiency. How much is Faraday efficiency? If there is any leakage, any current leaks, but in this case, we got very high Faraday efficiency, approaching 99%, with extremely good hydrogen purity. That is also important for the application, and that this was assessed at a single cell level. I would like to mention some relevant results, electrochemical results for the hydrolyte membrane. There were several versions developed by Hydrolyte in this project, and an optimized version of the hydrocarbon hydrolyte membrane was showing a performance of 1.7 volts at 1 ampere square centimeter. This was achieved with 1 molar KOH recirculation, just to be, let's say, just to provide a complete picture. And what is really interesting to see that the series resistance was so low. This is about 50-70 microns membrane, and this series resistance in this case is something like 0.06 ohm square centimeter. That is comparable to what is usually observed in PEM electrolysis. So a very nice performance in terms of conductivity for this membrane. And now moving to the next slide, another relevant achievement of this project is regarding the composite membranes, because also it was a key objective of the project to extend as much, or to explore eventually, the operating temperature range. And using these composite membranes with the Syria filler, we were able to achieve, at least in terms of polarization curves, so of course durability is another story, 90 degrees Celsius. Now, I would like to, I'm always happy to show you in these workshops this plot, this, let's say, comparison. This is an internal comparison in the same laboratory at CNR ATE. Is a comparison between PEM electrolysis performance and AEM electrolysis performance in a wide range of current densities at the same temperature, 50 degrees Celsius. This is shows very clearly that at the moment, in the same laboratory, we have a gap of about 300 millivolts at 2 amperes per centimeter for the AEM electrolysis technology. But I will also point out that using AEM electrolysis, we don't need any PGM. In this case, there are no PGM electrocatalysis, critical raw materials free in the AEM technology, especially hydrocarbon membrane instead of perfluorinated membrane. At the moment, you know, there are a lot of concerns from the European Commission about these perfluorinated materials. In this case, we don't need the perfluorinated materials, and especially titanium-free. We have used indeed the nickel bipolar plates, and our cost analysis has shown that the impact of nickel bipolar plates and PTLs is really impacting really much on the overall cost of the stack at the moment. Of course, there is a possibility to move to some steel coated with nickel, and eventually we can save further costs in this context. And you know, this comparison is done versus PEM electrolysis technologies using low loading electrocatalysts. Just to understand from where this gap comes, you can clearly see that is not from the AC impedance results. The NIPIS plot at the bottom, you can clearly see that the main gap is not related to the conductivity, to the series resistance of the membrane. It is essentially related to the polarization resistance. And of course, it is very clear and logic to understand because, of course, we have used the non-critical raw materials, nickel, molybdenum at the cathode, nickel iron at the anode. So in comparison to platinum and iridium, ruthenium, precious metal electrocatalysts that are used in the field of PEM. Of course, we understand that there are different applications, different possibilities for these technologies. Of course, I don't think we can really reach with the AEM electrolysis technology the performance of PEM. Because of course we are dealing with completely different materials, but there are different applications where each electrolysis technology can find possibility to be applied successfully. Let me move to the next slide. How many minutes? Another 5 minutes. Okay, good. Thank you. Regarding the stack development, we started with large batch MEA components preparation for stack assembling, 27, 25 components. We just to be, let's say, to stay on a conservative approach, we have preferred the catalyst-coated electrode. This does not mean that the catalyst-coated membrane was not explored, but this was much more, let's say, reliable for large area electrodes and membranes. So we have separate membranes with separate electrodes. You can see pictures of the anodes based on nickel iron, the cathode based on nickel molybdenum on PTLs and gas diffusion layers, and you can also see the durability of these large area MEAs on a 200-250 hours test. You can clearly see that at the very beginning of the test, you have a loss of efficiency, but the performance is quite constant after this initial, let's say, decay of performance, and also possibility to cover a wide temperature range. Now, for what concerns stack engineering, this activity was carried out by Cummins here in Belgium, in AEMEL, and They started with the computation of fluidodynamics and selected the appropriate materials components. As mentioned, bipolar plates are flow field bipolar plates, and the PTLs are essentially based on nickel, and they made a lot of leak test, pressure test, and you can see a picture of the stack here at the Hydrogenics, and initial testing was carried out at CNR IPA. You can clearly see that for these initial tests, we have not used a complicated or complex balance of plant, just a very simple system with KOH recirculation at the anode. First, we tested the vertical configuration that was not much successful with a lot of diffusion issues. This is a 2 kilowatt stack with KOH feed 1 molar at a rate varying from 0.5 to 1 liter per minute, and we got much better results after good conditioning period, after using the horizontal configuration, and with some back pressure we were able to pressurize the stack. These results will be discussed much more in detail by Hydrogenics. I will just say that we have not fully achieved the, let's say, the objectives that we have promised, but we are close to these objectives, to these quantitative targets. The average cell voltage was 2.1 volts at 1 ampere square centimeter with 1 molar KOH recirculation at 1.25 milliliter per minute per square centimeter at 50 degrees Celsius. That means operation at 100 ampere for the stack. And yeah, this was lower than what we have promised, and especially if you look to the voltage efficiency, this is something like 71% versus the high heating value of hydrogen at 100 ampere, compared to something like 86 that we promised in the description of action. And good results for the Faraday efficiency. We were able achieving the capacity that was indicated in the description of action. But energy efficiency is, of course, a combination of voltage efficiency and Faraday efficiency. And at the end, we have an energy efficiency approaching 70% versus the high heating value, compared to 80% that was promised. Of course, all these results deal with an operating current density of 1 ampere square centimeter. So comparison with efficiency of alkaline systems should be made at the same operating current density. Regarding, of course, the capacity, this was demonstrated. Durability is tests are undergoing, and we had good results at the very beginning. Some degradation was observed, and we have indeed developed 2 stacks. One first stack to start with this first trials in order to understand the issues. So we got some high ohmic resistance, and this was affecting all the achievement of these values, of these key performance indicators. The new stack that was assembled after receiving a feedback from the characteristics of the first stack. We have measured the series resistance, etc. We have used electrochemical diagnostics to understand the behavior. And the new stack is in principle less affected by these issues, and will be tested until probably as also after the end of the project as follow-up of this project, continuing the collaboration with CUMMINS. And just a few words about the dissemination and communication activities that we have performed. We have published 4 papers in open access journals. Of course, there are a lot of papers we aim coming in the next months. So we have accumulated so many results, especially with these new membranes, the reinforced membranes, but I also will say about stack testing, etc. So we expect some additional papers in the next months, and especially we have participated to a large number of conferences. And I would like to mention also the collaboration with the other two projects, the project Chanel and NEWELY. Especially, I would like to thank the coordinators of these projects that have, let's say, collaborated with us in preparation of workshops, and also in this AEM hub that was launched by one of these AEMEL projects. So this was let's say a nice outcome from these three projects. This strong cooperation, and I hope this cooperation with the other two projects can continue in the future, because of course we need to progress together to achieve the important results that we expect in this field. Regarding our website, we had an astonishing number of visitors. Probably someone was attracted by the curiosity, probably, we don't know, but at the moment Google Analytics says that we have really an incredible number of visitors. Exploitation activities regard especially the main components developed in the project, and with this I would like to thank you so much for your participation to this workshop, and the Clean Hydrogen JU for all the support that have provided during this period, during the project running period, and thank you so much for your kind attention.
Thank you, Professor Aricò. Are there any questions before we move on? I wonder if any questions came on Teams. There are some questions in the chat. Let me see.
Pierre.
Okay, Pierre, maybe we start. You can press the microphone.
Yeah, thank you. Very interesting. Did you measure anything related to hydrogen crossover during operation under pressure?
Essentially, we have measured the Faraday efficiency. We have measured the hydrogen flow rate at the cathode after drying, and we have related this to the Faraday efficiency. We have not measured the hydrogen concentration in oxygen in this case because of KOH. KOH is damaging our gas chromatographs. So we have preferred measuring the hydrogen flow rate at the cathode related to the operating current density according to the Faraday law. We have estimated, calculated the Faraday efficiency that was 97%.
And maybe a question from the chat: what is the reason for improved performance over durability test?
Yeah, this is an interesting question because, of course, at the very beginning of the durability test, we have some loss of performance that we attribute to some conditioning change of oxidation states for the electrodes. But with time, we have observed a continuous improvement that could be related to the cleaning process in situ, because there are always some carbonation phenomena. We need to point out that we operate in an alkaline environment, that there is some CO2 uptake from the atmosphere, and during the electrolysis operation, of course, this is removed, and the hydroxide conduction becomes largely prevailing. This is an aspect. Of course, in some cases, we have also seen some membrane thinning with some small decrease of series resistance. This is another situation that was observed in some cases, especially in durability test of 2000 hours in the single cell. This is another aspect, but I would mention these two aspects as let's say the most relevant for explaining this improvement of performance with time.
Excellent. Thank you very much, Antonino. And now let's move to the next presentation, which I believe will be given online. I hope we have the coordinator of the channel project with us. Indeed, Luis.
Yes. Hi. Can you see me? Can you hear me?
Good morning.
Morning.
We can't quite hear you, Luis. And
Yeah, I apologize. I am very sick. Yeah.
this could be a bit of an issue on how we can. Now try again.
Hello, everyone. Good morning.
Yeah, perfect. Excellent. So, Luis, the floor is yours, please. You're welcome to. You want to share your screen?
I think will be easier. Yes.
Yeah, perfect. Go ahead.
I will do that. Meanwhile, I really apologize, everyone. This I sound a little bit weird. It's because I am quite sick. Now, I will do my best that you can follow my presentation. Just let me know if you can see my screen. Can you see my screen?
Yes, that is perfect.
Great. Thank you, Nico. Okay, thank you. I would like to thank you to Antonino and Nico for the invitation to this workshop. I strongly believe that it will be a good interaction over the day. Unfortunately, I cannot be there, but we have some colleagues attending on behalf of channel. As I say, really sorry is I cannot sound a little bit weird, but I'm a little bit sick. So I will introduce a channel, which is basically a project dedicated to the development of the most cost-efficient hydrogen production unit based in ANIONE membrane. I am Luis Colmenares. I was a deputy coordinator of this project. I belong to the SINTEF industry, to the group of batteries on hydrogen technologies. This project was a joint effort between the Norwegian Technology and Science Universities in Norway, the Forschung Zentrum Jülich in Germany, Evonik also in Germany, with advisor from Shell in Netherlands, and involvement of the ENAPTER in the development of the stack and exploitation plan. And the new Jülich was focusing the catalyst development, optimization, catalyst layer, integrations, catalyst layer, and single cells. And Evonik was in charge of the development of the IAM. Meanwhile, SINTEF was in charge of the coordinations and characterization of catalysts and single cells, optimization of the breaking in and characterization procedure together with Jülich. So the main objective of channel was to manufacture a 2 kilowatts AEM water electrolyzer based in PM-free electrocatalyst, also cell components like porous transport layer bipolar plates, operate in differential pressure, and had a performance at 1 ampere per square centimeter below 1.85 volts, in at least in 1 molar KOH, or less concentrated KOH, and also in the inside water. The target was to have a system with capital cost below 600 euros per kilowatt. That is a project that recently finished in June. We have this support for the clean hydrogen to execute this project, and we was working a low TRL between 2 and 3. So to disclose this main objective, channel was highly focused in the development of the state-of-the-art Evonik polymer materials. Development of the membrane of the ionomer, the anion SN ionomer, according to the KPIs set in the fuel cell on hydrogen undertaking by 2019. In addition to that, we were focused heavily in the development of nickel-based electrocatalyst for the hydrogen evolution and the oxygen evolution. That was one of our main outputs of the project, focusing on optimized catalysts that had, how you say here in my slide, at least and performance on over potential below 150 millivolt in the hydrogen evolution, ex situ characterization, in this case for rotating this electrode at different concentrations of the KOH. Meanwhile, the oxygen evolution, our requirement was to have an over potential less than 300 millivolt at 10 milliamp per square centimeter at different concentrations KOH. Also, the long-term ex situ degradation of this catalyst was investigated. In addition to that, we also invest a lot of time to integrate those catalysts and the membrane ionomer in a functional single cell in order to achieve less than 1.85 volts at 1 ampere per square centimeter, optimization of the in configurations CCS versus CCM, and the procedure to functionalize an optimal single cells was in place. Especially also, probably you will see later in the day with another of our colleagues from Channel presenting about the protocol that we try to implement to validate our concept in the single cells configuration. Finally, we design and integrate all the components in a small stack, achieving 2 kilowatt stack. Operating differential pressure try to keep the same performance that the single cells was giving. And finally, we assess the cost and CapEx of the development. So summarizing what we have achieved related to the membrane ionomer development, the membrane ionomer development per se, we have able to achieve mainly all the requested KPIs. Nevertheless, during these optimizations, we try also to contribute to understand the different methodology to characterize that membrane on specific conditions. Not only in situ, one of the gaps that probably we need to address in the future is how to characterize properly the properties of the membrane ionomer and in situ configuration. Also related, what will be the stability of the membrane and the role of the ionomers on the stability of the single cell, for example. So we explore also different thickness of the membrane, but we was dealing related to mechanical stability on hydrogen gas crossover. That's something that we also implement in Evonik to characterize hydrogen crossover and try to understand how to minimize that. We didn't reinforce the membrane. Nevertheless, we achieved to have a good performing AEN or ionomer to be implemented in the stack. As I say, one output or takeaway from this development process is we need to understand in operando the stability of the membrane. Related with the catalyst development, as I say, we highly invest time in the catalyst development, nickel-based catalyst, nickel molybdenum with carbon and nickel iron. We achieved our target related to the over potential at a different concentration of the KOH, as you can see here in, I don't know if you can. Yeah. I just see here we characterize the performance of our catalyst at different concentration of KOH, also a different amount of the ionomer on the catalyst, in order to understand the correlation between the ionomer content and catalyst performance. We was able on that configuration to identify our best configurations and related to the ionomer content and concentration of the KOH. We was able at a different concentration of KOH related to the hydrogen evolution catalyst, sorry, able to achieve the state of the art. Also related to oxygen evolution compared with nickel oxide, we are able to perform better on the condition determined by Channel. So the takeaway from our side is that we need to learn more about the correlation ionomer catalyst performance. We need to try to develop an in situ characterization of the catalyst to understand or to determine the active electrochemical surface area in situ. That will be allow us to understand better the radioionomer catalyst activity. Also will be help us to understand the relationship between ionomer content and concentration of the KOH. That's something in the end of the project we identified that had to be properly optimized the ionomer content, a function of the final electrolyte concentration that we want to implement. So knowing already the performance for the hydrogen evolution, oxygen evolution catalyst, we integrate those materials together with the best performing anionic shell membrane, generation 3. As you can see here, this cross represent the target from channel, 1 ampere square centimeter, at least and voltage at 1.85. This target was why achieved concentrations of the 1 molar and 0.5 molar KOH, but the loss of the performance was observed assume the concentration of KOH was below 0.5. There's a lot to learn here, still a lot to learn here, because also, as I mentioned before, there should be a correlation also with the amount of the ionomer in the catalyst layer. We need to understand better the role of the ionomer catalyst layer as a binder, as an ion conductive, identify the thresholds related to concentration of the electrolyte and amount of the ionomer. We were very much reproducible, assume we identify the amount of the ionomers at the concentrations, that's in 1 molar KOH at 60 degrees. We was able to be reproducible in the manufacturing of the catalyst layer and the stability of the catalyst layer where the ionomer play a role. And that was something also that we observe in our manufacturing process. Probably my colleague from Julius can explain better later in the presentation, in the afternoon session, where we try to identify the threshold between the mechanical stability of the catalyst layer given by the ionomer and the effect of the ionomer in the losing activity a certain amount of the ionomer. Yes. Finally, after that, we're learning a single cell, 2-cell stack, 5-cell stack. We integrate a series of cells in 1 2-kilowatt stack. Unfortunately, we didn't achieve our goal related to the stack. We can now operate the stack at differential pressure due to the high hydrogen crossover. We had a lot of such issues related with the mechanical stability and also electrical contact in the design that affect directly the applied current. As you can see here, we was only able to test about 250 hours our stack, but using a very low current density because the huge overvoltage that was having in our stack design. So unfortunately, we fell in that target. Nevertheless, this was a good learning process related to how to transfer execute optimizations, single cells performance into stack device. Summarizing, we are also proud that we achieved a high-performing electrocatalyst that we would like to investigate further and to implement in more optimal stacked systems. We learned or established some background related to the membrane and ionomer characteristics and properties. Even so, we need to go more in deeper understanding of those characteristics in operando. We was able to optimize our catalyst layer manufacturing and integration of the catalyst and single cell, achieving the requested target that you see here, 1.85 volts at 1 ampere per square centimeter, showing good stability over 1,000 hours at this operation current density. Even so, we was not able to achieve the stack. We did theoretical study related to the cost of the system basing the properties of our catalyst, basing in the knowledge of the stack related to the system development, where we estimated that our finding related to the catalyst and membrane can be integrating appropriately stack design in a time frame of the 3 years, achieving the cost that we was targeting. If you want to learn more about our findings, here there is a set of 5 publications that we have. We also have 2 publications that are in the revision process related with the catalyst layer, and also with the nickel iron from our colleague from Julius. Those manuscripts will be published soon. So I invite you to have a look at those publications to understand more about our material development, understanding, and characterization. With that, I thank you to the organizer, Antonino, also to our project officer, Nico, for the invitation, and to all my colleagues in channel with the contribution to this project. And thank you, everyone, for your attention.
Thank you, Luis, and I wish you. You can hear the clapping, and I wish you quick recovery, and thank you for your stamina in giving this presentation. I wonder if there are any questions to Luis from the people present or the people online. Seems there is. Okay, throat longees, and Luis, maybe you can read it. Were you using CCS or CCM formats?
Yeah, okay. We tested both, but the configuration for the stack on single cell was CCS. Basically, the same explanation that Antonino gave. We didn't find a huge difference in the performance between CCM and CCS, but let's say the better reproducible procedure to prepare the catalyst layer, we stick to the CCS.
Right, thank you.
You're welcome. I want to say also, Nico, is something more deeper in that aspect. Our colleague from Julius and my colleague from SINTEF are present in the workshop in the room. They will stress more that aspect later on.
Perfect, thank you. There is another point, maybe we can answer this as well, Luis. Maybe you can read the question. Yeah.
Yes. Yeah. How the rotating this electrode performance relate to cell electrode performance? Yeah. I mean, I will not say that's a one correlation, but at least it's an ex situ screening procedure. They allow us to identify catalyst activity, and investigate in ex situ the composition of the slurry related to ionomer content, effect of the ionomer content, electrolyte content. Of course, there is no a one-to-one transferring, but at least it's a good basic understanding of what is the activity and correlation of the ionomer and electrolyte related to the activity of the catalyst layer. We optimize a lot our different compositions of our catalyst in rotating this electrode related to the composition, different synthesis procedure, reproducibility, based in the response of the rotating this electrode.
Thank you, Luis, and once more, wishing you a quick recovery.
Thank you.
Right, we will move on. I'd like to invite Aldo Gago to join me here. Let me try and so I think this is presentation number 3. NEWELY. Perfect. Yeah. And let me just link this. This is a PDF. Oops. But for full screen. So, first of all, am I sharing my screen or not yet? I'm not. So let me share. Slowly. Okay. And then maybe this will do it.
Yeah.
Oops. Taking a bit long. I can pray.
Otherwise, if it's not in full screen, I think it's big enough. No? Don't have any small letters.
Let me try this one. No.
No?
Okay, we'll have to do with this, I guess.
Yeah. Okay. Well, first of all, thank you, Nikos, thank you, Antonino, for this invitation. My name is Aldo Gago. I'm coming from the German Aerospace Center, DLR, and I will present the project NEWELY, next generation of alkaline membrane water electrolysis with improved components and materials. So here are some facts from the project, where it started, and the budget. As you can see, the budget is it has about 300,000 more, 300,000 euro more than what by that time FCGU funded, and that's because we have a partner from South Korea. The objectives quite similar to the previous projects, right? Develop new components with improved properties for anion exchange membrane electrolyzers. So redefining all of them from membranes, ionomer, catalysts, PTLs, and the performance also similar to the other projects, 2 volts and 1 amp per centimeter. But initially we were targeting operating with pure water. That was our initial target. And we had a risk mitigation plan that if by half of the in the middle of the time of the project we did not achieve our performance, then we will use KOH. And that was the case. Operating with pure water is very challenging, and we require more funding for that. Here is the list of partners. So as I said, the project is coordinated by DLR. We have WHS, CEA, and there you can see as well what their roles. Company PROPULS, ELECTROLYSIS, EPK, SENMAT, MembraSense, and 2 other. These 3 last institutes, they were the membrane guys of 2 institutes from Czech Republic and the keys from South Korea. Here I show the concept of the project. So you can see 3 main blocks that it says AEM, electrodes, and stack. So those were the main developments in our projects. And you see a big logo from the partners, MembraSense, SENMAT, and PROPULS. So these are 3 SMEs. And I must say that as a coordinator working with them, the experience was very rewarding. So they really engaged in the project. They were following very closely with the other partners. It was really a very nice experience, how they're pushing the developments in the projects. And we have Air Liquide as well as a large company. They took care about the analysis that matters to a large company on cost and life cycle analysis. And you can see as well a small cell. I will talk on the left. I will talk more about that in a moment. Here you can see the quantitative objectives. So starting with the stack, it's the same power than the other projects. And initially, we were targeting 40 bar, and we had to come down to ambient pressure. The reason is because our initial goal was to operate with pure water, and we had a partner who had a test station that could operate at that high pressure, as this test station was used in a previous project that Nikolaos mentioned, Pretzel. But the moment we changed to KOH, we could not hold this pressure. We did not have any system for that. So this has been a nice experience. Someone,
Maybe you can ask them to mute.
yes, please. If someone is not mute, please mute yourself. Thank you. Also the cell voltage and the current, same experience as the other projects. We learned that AEM electrolysis can perform as good as PEM. They can reach similar performances. And as Antonino said, durability is another story. We carry out as well our durability test, 2,000 hours. This is about to start. This will be done in the stack, not in single cells. And in addition, all the other properties, or the membrane properties, were achieved and exceed. And the catalyst, it was also achieved, the overpotential, low overpotential, and the analysis studied by Air was also carried out. So now I'm gonna summarize the main achievements of the project. Regarding the membranes, I'm not gonna show technical data. As I said, all the membranes, there were several membranes developed in the project, several types, and they achieved the technical targets. But for me, the main highlight was the creation of a startup company. That's TaylorMem, a company that one of the partners, Jan Sita, created. There were several patents as well, and very successful, because now this company is selling membranes. So that was not planned achievement, but we're very proud of it. Also, the catalyst, we learned how to develop electrodes. The same as the other projects, our best approach was CCS. Seems that that's what works best in electrolysis. And we could achieve high performances either in laboratory cells from the partner, as well as in the cell from the partner PROPULS. Here is another very important achievement. So before integrating the materials on the stack, our partner PROPULS asked us that we had to validate all these developments in their own single cell hardware. I show on the bottom an image that they have now a more advanced model. And that was great, because with the test we carry out in NEWELY, in particular the CEA, we were able for the first time to validate a cell test hardware for AEM electrolysis. And it doesn't even exist in the United States. So this is, that was a very successful test. And now they've been selling the cell. It's been used in other European projects. Several people here already have them or have ordered it. So that was really a very important achievement. We have now a commercial test cell for AEM electrolysis that any lab can order from the company PROPULS. They also developed the stack from the design, the manufacture, the initial testing, and the quality control. So this is a real advanced technology stack, I would say. It's not just stacking plates and then putting bolts and nuts. It uses this hydraulic compression technology, which ensures uniform distribution of temperature and contact pressure. So the stack was just this week installed at the partner FPK, and is about to test to start the long-term testing, but already all the initial test and qualification process was successful. Also, another achievement in a project that was the design and construction of an AEM electrolysis test station for the partner APK, and also was in collaboration with partner PROPULS. And lastly, that was the LCA life cycle analysis carried out by Air Liquide. So they really investigate all aspects about materials, about the environmental impact, and very interesting analysis and the potential of scaling up this technology. And finally, these partners were very productive, especially the partners involved in membrane, 7 publications, others in the process of writing, and our project won the Best Innovation Award last year. The membrane is the key. I think it was called like that. So that was also, again, a nice achievement. With this, I would like to thank for your attention, and I'm open for any question. Thank you.
Thank you, Aldo. Maybe we'll start with the room. Any questions to Aldo? It's not. Let's have a look.
Yeah.
Maybe you can press the microphone.
Sorry. Well, it's for you as well as for the others. All these cells work under dry cathode configuration or double compartment electrolyte feeding?
Let's see. The most successful test was done by CA. If Frederick is there, he can answer, because we tried several times, dry cathode or wet cathode. Are you there, Frederick?
Yes, I'm here.
CA.
Could you hear me?
Yes.
Could you hear me?
We can hear you.
Okay. Yeah, I mean, most of the tests performed at CA was done in dry cathode mode, and on small scale size cell, it was 2 square centimeters. And we also performed some tests with both wet cathode and wet cathode, and also supplying the anode with KOH, but the difference was not that high. But so I don't know if it's a matter of the cell or something else, but the test we have performed didn't show a big difference between dry cathode mode or wet cathode mode.
Thanks, and thanks for the presentation.
Thank you.
Thanks. Yeah, there's a comment. I'm going full screen. We tried this, but one of these things that will happen. Sorry for that. So yes, I guess thank you once more, Aldo. I think already people following this workshop do realize that yeah, these projects started beginning of 2020, all 3 of them, and COVID came. So there were delays, there were some extensions granted to the projects, but indeed you can see that both projects have now finally come with the stack. Okay, ANIONE already tried a stack, but now there's a second one to be tested long term. And NEWELY is also now starting the 2,000 hours of testing. Still, we hope that the projects will be reporting after the end and completion of the projects in our trust database, in conferences, etc. So these results will not be lost.
Sure.
Okay, so let's now go to the next presentation, which is from PROPULS. Yes. Find this, and let's hope that we'll be able to go full screen. It's a oops. So that we sign.
I send it to you as a PDF.
It's a PDF, but let's see, why can't it see it? David, we have our technician here. Maybe it's the time for you to. It is in PDF, but no, it was almost there. Download. Oops. Okay. Right, so we're there. I don't know if I can go even better. F11. Okay, that seems to be good enough.
Okay. Good morning, everybody, and thank you, Nico. Thank you, Antonino, for invitation to this workshop. So I present our novel stack concept.
Sorry to interrupt, but
It's
I
not
can't
shared.
see the. Yeah, it's not shared.
Okay, sorry for this. Let's go back to Teams and okay. Try F11 again.
Can you now see the screen also online? Yeah. Okay, perfect. So yeah, my name is Ulrich Rost. I'm a member of the managing board of the company PROPULS, and yeah, I have the honor today to present to you our stack approach that we further developed for alkaline water electrolysis in the framework of the NEWELY project. So let me give you some quick words about PROPULS. PROPULS is a classic engineering office coming originally from automation systems for power stations, nuclear power stations, coal and gas-fired power stations. But as the conventional power station business is running off, we were also increasing business in hydrogen technology, in modern electrical energy systems for heating, for chilling. We have a customer who's busy with biogas, and also we were involved in several projects on automation of hydrogen demonstration systems. Yeah, software engineering is our main business, but as I mentioned, also hydrogen gets more and more a business for PROPULS, but also we do R&D in the framework of public funded projects funded by EU, by also by North Rhine-Westphalia. We get big support, and NEWELY is, for example, one of the clean hydrogen partnership projects where we have been involved. We have the mission to develop also our own stack technology and commercialize it soon. But at the moment, it is still a prototyping stage that we achieved. But it was already mentioned that based on our principle of the hydraulic cell compression, we already commercialized with our daughter company, ProH+, a test cell. And I will say some words to this test cell during my presentation. So it was already mentioned several times that PROPULS had the objectives in NEWELY to first of all develop a testing hardware that was provided to a German Aerospace Center, Westfälische Hochschule, FBK and CEA. So the scientific partners who were involved in cell testing were equipped with a test cell, with a hardware, to have one hardware platform where they can test the materials and the components developed in the project. Then PROPULS was together with Westfälische Hochschule, so Westfälische Hochschule took over the main work in this regard, but together with PROPULS and Westfälische Hochschule, the stack design was developed. It is a 200 square centimeter cell that we developed and a 5-cell stack that accommodates then later the active materials from the NEWELY project. And last but not least, we commonly developed with FBK a test bench, an alkaline water electrolysis test bench that comes already with all the functionality to either operate the test cell, the single cell, and yeah, these days we integrated the stack into the test bench at FPK to operate our NEWELY prototype. So it was already said several times that we follow a new stack technology that we call the hydraulic cell compression. So the hydraulic cell compression, I will quickly summarize what is this. So we have the cell more or less looks like a normal cell, like an alkaline water electrolyzer cell. But what is surrounding the cell is a flexible pocket. So we have here surrounding the cell a flexible pocket in this case. So I don't know if you can see this model. Yeah, it is a pressure housing where we can have a look inside, where we see the flexible pocket is made of silicone. So it is really flexible. So all the cells are inserted in those flexible pockets. And in operation, you fill up the pressure housing where the flexible pockets were inserted with a hydraulic medium. And if you now compress the hydraulic medium, if you raise the pressure level inside the pressure housing, let's say to 10 bars, you have 10 bars everywhere inside your pressure housing and transfer it nicely, smoothly, homogeneously over the flexibility of the pocket to the cell. So the cell is compressed all over with the same pressure, independently from the size of the cells or the number of cells that were inside of the stack. So here I put some images on the slide. That is pressure-sensitive film, pictures of pressure-sensitive film. You can see it is homogeneous, doesn't matter if that is 4 individual cells, so 4 different ones, and they all show the same cell compression distribution, and we did it several times with more or less hundreds of cells already in 4, in 25, in 200, 500, and 600 square centimeters, and we always find more or less the same cell compression distribution. So that ensures the homogeneous cell compression and avoids hotspot formation, for example. And furthermore, the hydraulic medium, if we take an oil or water, so a liquid hydraulic medium, then we can also achieve a very homogeneous waste heat transfer. So even at high current densities, the waste heat of the cells are homogeneously distributed into the hydraulic medium. And yeah, it is a stack platform, and you know, we realized already fuel cells. That was the beginning of our technology development. Fuel cells, batteries, and yeah, especially electrolyzer designs. For example, the alkaline electrolyzer that we built up in NEWELY project. So I already summarized the advantages. It is the increased stack safety because you can operate with little risk of hotspot formation. You can operate the cells at very high current densities due to the homogeneous operation conditions. Waste heat recuperation on system level could be achieved by taking off the heat from the hydraulic medium. And as I showed you here with this little model, it's very easy to assemble stacks because of the monopolar monopolar cell concept. So it's a modular stack device. So one last regard to the basic principle. So you can also achieve high pressure electrolysis based on this hydraulic cell compression by always achieving the constant cell compression difference between hydraulic medium and inner cell pressure. So by controlling the production pressure of hydrogen and oxygen. So first of all, we operated in balanced pressure mode, but we also developed lately a cell that could operate with up to 30 bars differential pressure mode. So you can raise the inner cell pressure and determine the pressure level and always control the hydraulic medium to be, let's say, 10 bars above inner cell pressure, or what is optimal for the compression of the cell would be also higher. 10 bars, just an example. So by this, we can achieve high pressure electrolysis. The cell keeps being the same. Just what you need to exchange is the surrounding pressure housing. So if your pressure housing is able to be operated at 110 bars, you can achieve a 100 bar production pressure. Of course, also if the membrane and the gas crossover are appropriate for this. So we saw that in Pretzel with a PEM electrolyzer, so we can operate this stack and the Nafion membrane with little gas crossover also at 100 bar. So that is what we used to build up the NEWELY test system. And what you can see here in the picture is what we, when the NEWELY project stopped, we further optimized the test system. And here's what is inside the test system. It is, I don't know if you can see that online. So that is the 2 half cells you can apply. So this is now PEM, yeah, but because I didn't want to bring nickel components. So there is a graphite cathode, that is a titanium-based anode. So you assemble everything and just clamp a CCM or a membrane if you use CCS approach. And then you can insert it again in your flexible pocket. So that's it. That is easily to make screenings, to perform tests on materials. Yeah, you can also, everything is modular. You see a little picture with all the cell components. Yeah, so into the frame you can fit the pole plates, the PTLs, and yeah, test what is your purpose, what you develop. If you want to make screenings on the pole plates, then you just exchange the pole plate material and use standard CCM and PTLs, for example. So here you can see the entire composition of our NEWELY cell that is also published in the proceedings of the EFCF 2023 this year, so where we published our last experiment in spring 2023. And yeah, what we recently developed here is a new interface between the cell and the manifold. So now we can also, the test cells can be operated at higher production pressure. You can clamp the cells up to 20 bar, but yeah, in the next weeks we will also try to achieve even more pressure on the pressure housing. We have here a single cell voltage measurement, and the power contacts were able to operate at up to 150 amperes. So if you use the 25 square centimeter slots, then you can operate this test cell up to 6 ampere per square centimeter. But we also have frames for the 4 square centimeter, then you can overload it massively. So to summarize our standardized alkaline water electrolysis laboratory device for round-robin test, we can achieve reproducible test results due to the controllable and homogeneous cell compression and temperature distribution. We have so far 2 frames for 4 and 25 square centimeter. Next step will be the development of a 50 square centimeter cell that you can also have larger cell areas. We have yeah, several powerful AEM cell settings discovered during NEWELY. There were SEER critical raw material free and also PGM based settings that we tested, and we were very proud that we can also supply PROPULS is the supplier for testing hardware for an EU-wide round-robin test in the framework of Sustained Cell, and where we, at this moment, build up the test cells for that. Here you can see some images about the tests that have been performed in NEWELY, but my colleague Frederick will explain that later on in much more detail. So here you can see the image of what finally came out. So based on the same principle, we have that stack design. We built up the 200 square centimeter 5-cell stack. to host all the nice materials that were produced and developed and produced in NEWELY. So it's now a stack concept that looks a little more than state of the art, but still has the hydraulic cell compression. So we have still single cells, and now the pole plates become part of the flexible pocket. So we have a very thin pole plate, and the pressure distribution is now distributed through the flexibility of the pole plate. So here between two cells, we have the hydraulic medium, and we overcome, let's say, the gap through the hydraulic medium by flexible spring contacts. And yeah, so we designed and realized an advanced stack platform to host the newly developed materials. And just to show that we have shrinking, dwelling, swelling membranes that always change their size. We have very sensitive new electrodes, and they change even the color sometimes. We have a very nice stainless steel mesh-based PTL, and we have those very flat pole plates that have integrated single cell voltage measurement, temperature measurement, and those spring contacts to get to the new cell. Just 1 second, yeah. So finally, we integrate everything into the stack. You already saw it here. It comes in a, let's say, in a micro system that sustains the hydraulic cell compression for traveling, because it was built up at Gelsenkirchen and then shipped to Italy recently. And to ensure that everything is operable, some preliminary checkups have been performed, like cell voltage, temperature checks. We checked the process media flux, stack heating, cell compression, and we also made some initial electrochemical tests in our workshop at room temperature. And we saw that all the 5 cells react electrochemically like we expected. And that was, the starting point after the successful pre-checks we delivered the stack to Italy, and now it is in the moment to start the 2000 hour test. Yeah, so I don't want to over expand the time. So that is just for us the start in the alkaline water electrolysis. We want to proceed to
exchange membrane.
And yeah, exactly, the membrane-based water electrolysis. And so we want to still focus on it, look for high pressure electrolysis, even scale up, like we found for the PEM 600 square centimeter. We even want to exceed that. We want to have a look for waste heat recuperation and stack operation at very high temperature levels to finally reach multi-megawatt stacks and discover the full power of anion exchange membrane water electrolysis in the future. So thanks for the funding. Thanks for all the collaboration among the NEWELY team. That was very fruitful collaboration with all the partners. And thank you very much for your attention.
Thank you, Ulrich, for the interesting presentation. Any questions?
Teams disappeared. Yeah.
Okay. Right. Okay, yes, we'll have something in the chat. So to use this hydraulic system in stacks, you're relying on a process system to ensure integrity of your pressure vessel. Curious about the safety implications of that.
So we use a standard pressure housing that is, that has normal pressure. So we get the certificate so we don't manufacture the pressure housing. So we buy it from a professional who builds up the pressure housing with, and we get all the certificates that it keeps the pressure. This on system level, you need to ensure the cell compression. So if you release cell compression, we have massive loss of performance if we recompress the cells. So we built up a little system that we call the stack management system to always control and always to ensure cell compression on the cells.
Perfect. Thanks. And a question in the room, you're welcome to press the microphone.
Thank you very much for these insights. I was also wondering about this deck design itself. Sealing is also a big challenge, and now with the hydraulic liquid in the stack as well, we have even more points which we can need to seal properly. Did you encounter any challenges in this?
Yeah, we work now 20 years on this technology, and that is mainly the core issue of the engineers to find a well-working gasket package. Here it was one challenge was to change to EPDM gaskets. So we come from the PEM world and always used FKM, and now we have new materials and find new settings, new packages, new structures. So, but now we have that flat gasket system that works very well, and we were really happy that finally we found something to tighten everything. Yeah.
One more question.
I was wondering what the cell thickness is in stack. What's the cell to cell distance?
Cell to cell distance.
Yeah.
We have a gap of less than 1 centimeter.
In between the two cells.
Yeah.
Okay.
So the hydraulic medium that flushes through the cells has a space of below 1 centimeter.
Can you make it thin?
It depends a little also on how much waste heat you need to remove.
Yeah.
Yeah, so that is the design issue.
Perfect. Thank you. So, right, now, the next presentation was to be from ENAPTER. I don't think we have a speaker from ENAPTER, so we'll go to the last presentation of the morning session, which is from Sebastiaan Herregods from CUMMINS. So let me start by sharing the screen. Okay, and then going to quickly this one. Let me try first to find the presentation. No, it's okay. I'll need to go back and find presentations. So, yeah, getting there. Fine. So it's number 5. No, sorry, it's number 6. Oh, no,
I was quite late with
you were late with
yeah,
sending
but
it.
I have it open. I
You have
can
it?
forward
Yeah.
it you by one click.
Perfect. Let's do this. Sorry, we're didn't get this on time.
You should
Okay. It arrived, being scanned. Sorry for this delay. It's a large file.
It's a PDF.
No, it's a PDF.
Yeah.
Okay, we have it.
Voilà. 2 megabytes.
Only, yeah. Right. Okay, so back to Teams. Sharing. Fine. Let's see if I can again make this F11. That work. I guess this is good enough. So the floor is yours.
Thank you, Nikos. Thanks for organizing the workshop and giving us the opportunity to present the results we achieved in the ANIONE project. I'm Sebastiaan from Accelerate for iCommins, and now we'll discuss the stack engineering and results. Maybe a short introduction on Accelerate iCommins. Accelerate is the new zero net emission technologies business unit of the company Cummins. And Cummins is a big multinational, mainly focusing on diesel engines, power generations, components, and distribution. That's their main business. In 2021, we are about with 60,000 people, and now a few years later, we are about with 73,000 people, and about 1.1 billion we invest in research and development. So the new business unit combines all our zero net technologies, like the electrolyzers, which was of your interest, of course, or fuel cell systems. Recently, we integrated some of these fuel cells in the Alstom hydrogen-powered train, the first in the world. Electrified components, so lithium-ion batteries, and internal combustion engines for hydrogen as well. On the bottom left, you can see our two stack products that we currently have. One is an alkaline stack, a relatively small size with about 87 kilowatts, and the other one is our main product, our PEM stack, which has the biggest let's say, product portfolio, and it's about 2.5 megawatts. From technology reasons, we're interested in both. For technology screening, of course, we're also looking forward to novel technologies like AEMEL. But currently, our main focus is on alkaline and mainly PEM, and we're extending our facilities over the last few years. We duplicated basically our production facilities by putting a new plant in Spain and by upgrading our plant in Belgium, which is also partially funded by Flanders and the European Union. Thanks a lot for that. On the project, like all of us, we were aiming to deliver a 2 kilowatt AEM cell stack and electrolysis system for AEM technology testing. We aiming at a 10-cell stack with an active area of 100 square centimeter, aiming at current densities of 1 amp per square centimeter at a potential of 1.8 to 2 volt. We have some efficiency targets and of course also the durability testing. Our cell stack design is based on a flow field free design. We did all the mechanical calculations of the torque and the finite element analysis of our structurings. And the end flanges are calculated by the ASME regulations. And it's a relatively simple stack design. This is an explosion view on the bottom left of a single cell. It has a double sealing mechanism. At our bipolar plates, we have an holding sealing, but in between the MEA and our, what we call structurings, let's say a frame of the cell, we have a gasketed seal. In the middle, you can see the MEA itself. Here you can see some pictures of our stack assembly. This was our
first attempt of the full stack, so 10 cells, about 100 square centimeter active area. And during the third assembly, we had some challenges with, let's say, wrinkled membranes due to some extra swelling occurring from the chloride to the hydroxide exchange of the membrane itself. Nevertheless, we assembled it, but in our second stack build attempt, we manually reworked these membranes a bit. We pre-assembled the MEAs to one component in order to enable the assemblies and the contacts in between the membrane and the electrodes. This is a cathodic coating support, the CCS approach that we did. Seems to be much better, but the data of that is still pending. So after the building of the stack, we of course first pressure tested it up to 35 bars for the full stack. This took typically a bit longer than we expect because we had to repressure, add extra water in the system to really achieve the stable 35 bar, which in this case was after a few attempts. And this might be related to the very hydrophobic nature of one of the catalytic supports. Then we started stack testing due to a delay in our test facilities. We first did this at CNR at the Antoninos facilities. Thanks a lot for that. We first testing it at vertical configuration with recirculation of the KOH at the anode while the cathode was dry. In this vertical orientation, we see quite large mass transfer limitations, but these were overcome by going to a horizontal configuration in this design. Basically, the gases are better allowed to escape the cell. So at this stage, we have achieved around 2.2, 2.25 cell voltage for the stack. And if you look at the best cell, it was a bit better. In the next phase, we optimized the flow rate in order to improve the mass transfer limitations. And basically, we got an increase by increasing the flow rate from 0.5 liter to about 1.25 liter per minute. And at this stage, we have a cell voltage on the stack around 2.1 volt, where the best cell is performing around 2 volt at 1 ampere square centimeter. Since we couldn't do the full pressure testing, but by just a simple adjustment at the laboratory setup by installing a back pressure valve, we could do some partial tests up to 8 bar of differential pressure. In this case, we can see there is a bit increase in the voltage, but this is mainly associated to the effects of the Nernst law, and there were no really drastic increase in mass transfer issues. So it seems quite promising to also operate at higher pressures. In this first stack, we also did some durability testing. In the first week, it was relatively stable, but unfortunately, in the second week, we saw some voltage increase in the second week. And we think this is related to some potential membrane damage due to the wrinkling of the not so optimal assembly of our first stack. And we hope to overcome this in the second stack, which we will start testing in the coming weeks. So in a nutshell, we reached around the stack performance. We have around 2.1 volt at the stack level at 1 amp per square centimeter. The best cell is a bit better performing. We did this at 50 degrees Celsius with 1 mole KOH recirculated at the anode. The voltage efficiency was around 71%, which is a bit below the targets we achieved. Nevertheless, stack capacity was around 0.4 normalized cubic meters around, which is in alignment with the target. The Faraday efficiency was around 97%, and the entire stack efficiency was around 69%. So that's something we'll need to improve for the future. And the stack power of 2 kilowatt was reached. And so for the coming months, we will disassemble the stack to maximize the learning of this first stack, and our second stack with a better assembly, with a better membrane to electrode contact, we'll start testing soon. So thank you all for the kind attention and the opportunity to present, and to the entire consortium for the fruitful collaboration.
Thank you, Sebastian. Magic here to see if there are if the presentations will be shared. Well, we are actually recording this workshop, so you will get a full recording for the presentations. Any questions maybe from the room to Sebastian? Yes.
From your personal experience on this project, how easy would it be to scale area or number of cells, given your experience?
So for our stack, the stack design itself, it should normally be quite scalable. It's more like the let's say the membrane stability and mechanical integrity at large scale, and maybe uniformity of membranes, which I would think is the first one to overcome.
Thank you.
Right, and with this, I would like to thank all speakers of this first part of our workshop. We will have a 10-minute break. Just to summarize, we saw the 3 anion exchange membrane projects. We heard from the coordinators, we heard from the electrolyzer OEMs involved in these projects. You saw the targets. We got there partially. That's a part of low TRL research projects. And I think we sort of managed to do a workshop using my personal laptop. And I'm a bit stressed with all this. And I realized I didn't even introduce myself at the start. So I'm the project officer at the Clean Hydrogen JU following these 3 projects, among others. My name is Nikolaos LYMPEROPOULOS. And with this, I think we can have a 10-minute break. We'll be back at 11 o'clock. Right, so Thomas, it's going to be you seated here, but maybe I should be helping you in your presentation is number 7. Then we have this is number 8, and then number 9 development, and then we go to 10, 11, 12, 13, and 14. And you need to toggle between this. I mean, I can help you bring the PowerPoint or PDF on screen. And maybe the presenter sits here. We'll see how it's going to work. Or you bring one more microphone. You can sit. You can even sit there. Use this microphone that the presenter is also going to use. And then I can sit here and play with the PowerPoint, mess things up.
We can push it.
Yep.
Okay, we haven't met before. I'm Felix, one of the people presenters. Say hi before. Speakers. Oh, yeah, because we're just speaking the same way. I'm from Ulrich. You guys speak for we'll just have it the same. Out of IRD, yeah. Yeah. Nice. It's not a thing, but different side. Yeah. I think it was a long time. Was in the center, but before we were in the line, a long time ago. That was when ECM was
Yeah.
Geerts. It took them all the electrical startup, hydrogen collector, CTO, hired.
Yeah.
After those two cells in next time, they didn't want to technology, we got Mamamea and glass fossil project and funding. Went to with for lots company with really shows project with the Olympics and back to you half hour and now chef. The chefs are now the reminds of how we suffer confidence. But give them all of those and those things.
Yeah.
As part of hydrogen around the room, it was outside finance.
Yeah.
And now it's electrolysis. We have a pretty big chemical company. I've seen it.
Yeah.
I know it's
But are we going okay?
yes.
Yeah, don't think it's.
And that's why you need your space facility.
Yeah, exactly. Yeah, it's everything. It's manufacturing. But of course, technology is not there. And it's not a control, you need to become more not service. So that's all the comes at the same time. So that makes it.
It's a safe for everyone.
Yeah, that's what everyone. You don't plan. Then it's you have more time to focus on that. Let's say. All these different questions will come. And then similar like this, it's all off the shelf and plug and play and if it if you have some delays there, then that impacts also the
Taking the barrier from 1 megawatt to 100, that's a major financial step.
Yeah, exactly.
Yeah. Like a hammer.
Yeah. And that one, because it's the commercial behind with these companies. According to my surprise when I joined the country, it's still depending on focusing on engines. Because it's in 2,000 people on the from 4 years. Yes, exactly.
ANIONE hydrogenics.
Yeah. It's and transition is always it's a challenge. Taking the first step, let's say communication challenges of okay.
Did you join before or after? Okay.
Yeah, in the middle of this project.
Yes, yeah.
So some of the initial overtime transition was already done, and we can slowly start that.
Just
Yeah.
I can't imagine it, and it was American style. I was German. It's ignored. We kind of so it could be an option too.
Yeah, for example, that's for the youngest, and if you can imagine this getting maybe some ideas. In order to get it like this, it takes a while to find that this. Because
The structure.
let's say that
Stabilizing and which as well. From the beginning, that would have been
yeah, I think that people might think it lost. Yeah, something like you want to suggest with good ideas, but you don't put it on the right desk, then it's not gonna right? Yeah, it takes a
And
while.
now we're fast growing. Yeah, we need to give good support to the.
Yeah.
That's also in the past 2 years. Sorry, I'll mention that.
Yeah. But of course, the point of the business is always somewhere. There's another thing. So. Nobody's looking. Yeah. Everything is a visual. As a scope. Yeah. Then I showed you a piece of handling. I'll be not have to change shit. If you try to explain that in the presentation, you can edit. You give them the compliment and you say, now I understand what the challenge is. Everyone was that's part of the struggle. Yeah, exactly. Everybody is basically working with problems where not sure what really is if they and literally all the team and does everybody knows what it was now. We need to have computer cells, everything else, all different shapes, everything's now 300% session. Yeah, I can exactly. One person like, oh, let's take a coding line due to a course experience. Experience. Want something more than less. I think we're going to change to the objective. Typically, active area now is 2 A3s. I'm very mindful of 2 A3s for this. It is exactly what your outline is actually. So, likely 37 meters. And then also for the term and let's see you've got achieving only 7 minutes or change the ball for. So maybe you would like to take your slides. Yes. For I'm talking so much. Then we saw it out with the work together.
So this is you need to say next slide, perhaps, Thomas, and I go to the next slide, or you want to?
Yeah.
Say next slide. But no, because I have the camera on and.
We'll sit here. And my next slide, I was here.
Next slide, or you try the 2 fingers there. Oops. First slide page, then I don't quite work. So that is with 2 fingers. You can press now the microphone, you can start.
So we continue for the next session. Right, the others. Okay, Thomas.
Yes,
That's in this week. Yeah.
Yes, it's being shared.
So, the next session. First of all, my thanks goes to Nino and Nikos to have the possibility to conduct this this session here in this workshop, two-in-one workshop. Thanks for organizing it. What is the actual aim of that session now? So we will present, get some presentations, and then in the afternoon we make some discussions. So the whole thing is actually a deliverable from the JRC towards the Clean Hydrogen Journal Undertaking on a report on AST protocols for low temperature electrolyzer. And this deliverable is in two parts. The first part is what we're doing now, the session, and there will be a small report made of that. But the main part will be a report on a proposal for AST protocols of low temperature electrolyzer. And it will cover all three technologies, so alkaline, anion exchange, and PEM. So this report, which we're writing and which I have distributed a draft version on the 8th of September to about 250 experts in the field. So probably have received that as well. Where I ask feedback, comments, and of course this is only possible to draft it and to write it and to make the report possible with the support of the partners, and some of you are here. So what is it all about? So we want to have a proposal for EU-wide, EU-harmonized AST protocols for assessing performance degradation in stacks of low temperature electrolyzer, water electrolyzer. Again, this goes for all three technologies, and that is in different application areas, power to hydrogen industry process, electric energy storage process, and so on. Using to produce green hydrogen, using renewable electricity. So that's the aim. That is what the AST protocol should actually say the context of it. So it's not intended to replace any other existing protocols, but to allow for an objective comparison of test results from different projects or research activities, and using well-defined reference conditions and representative operation profiles. So just let us remind on the different definition of what an AST is and what an accelerated lifetime testing is and what accelerated stress testing is. So mainly the only difference is between them, that is the ASTs are basically intentionally non-destructive, and they aim at triggering the same performance degradation mechanisms which presumably occur when you expose the stack for longer times under normal operating conditions, rather than stressing operating conditions. What the stressing operating conditions are, what we took up in the report, I will just come to that. And in comparison to an old, it is basically the old is basically you not aim, but in the end you end up with destroying the stack or failing the stack. But the AST is not. So that is about the report which I have sent out on the 8th of September to ask for feedback and comments. And yeah, it contains what we think what we should have in there. If you have comments, please write to us. And I have set deadline on the second week of October. So not next week, but the week after. And then we should have a public stakeholder consultation on the joint undertaking website in December. And then we think we can get that publication early next year on that. So the report has different stressing operating conditions, and that is basically operating at high temperatures at an increased differential pressure, ionic water impurities, and using real-world renewable power profiles from PV and from wind. And that is profiles which have currently, the original profiles are coming in a time resolution of 15 minutes. And the accelerating factor is there to compact them to less, far less. So say to squeeze 1 year into approximately 1 month or even less of operation, provided that the test equipment used to test the stack is capable of doing that as well. So this is the profiles that have been taken from the Belgian grid operator, and that's yeah, a random selection of 1 year of profiles. Very recently, you see it goes from the 5th of August to the 4th of September this year, and that goes for the PV. That goes for onshore wind and offshore wind. Basically, what was in the grid for these 3 categories in the Belgian grid. And the aim is now to compress them, to squeeze them together time-wise, in order to have an operation profile so that you have in a very short time, you expose the stack to all the power it will see in 1 year. And of course, you can get from these profiles also the daily profiles. So what we evaluate then, so what I said to you is compression factor. So you multiply the profiles in terms of duration by a factor, which I call F compress, and with a factor between 0 and 1 to fix the duration, and then in intervals you do an assessment on the performance, and this you do under reference operating conditions. So basically is a correlation curve, and if you wish also an impedance. And then you calculate the voltage, stack voltage deviations, stack power deviations, and in absolute terms, in relative terms, and also in terms of a produced cubic meter or a kilogram of hydrogen. And similar with the deviation in stack power. So in terms of milliwatt per hour or in per cubic meter per kilogram of hydrogen rate. Additional KPIs are the deviations also in the ohmic and the area specific pulsation resistances, absolute and relative, as well as the deviation in energy and electrical efficiency, relative and absolute, with a higher heating value or lower heating value expressed. Right. So this is basically what I wanted to present here. For the afternoon session, I have made some questions with the same presentation. Any questions? Yes, right.
Thanks for this. I have a question regarding the difference between AST and ALT. Looks to me that ALT is just a matter of time of the AST. So you are trying to enhance the degradation mechanisms, and the longer you enhance them, or depending on which one you're trying to focus on, you will then end up with the end of the lifetime.
The ALT is basically a test with kind of durability test. You set your conditions and then you run the stack for as long as it takes in order to see what you can achieve for the stack life, or if you set some criteria until the criteria are met. For the ASTs, you basically have you want to shorten your test time. Yeah. So that's basically you take a cycle and you shorten your testing time, because tests are expensive to run. And if you want to have a test equivalent to 8,000 hours, you don't want to run 80,000 hours or 120,000 hours, whatever. But you do it in a couple of weeks, or a couple of weeks basically. And you can do that by selecting different stressing conditions, and there could be one is the cycle, and you squeeze them in time. You can also squeeze them in or vary them in terms of power, so you can go to more than 100% power. You can combine different daily cycles to squeeze them together. So they have more seasons in it, because the daily cycles are a bit different in the season: summer, winter, autumn and spring, especially PV and wind also. Not so much for offshore wind, but onshore wind, they're also different in the seasons. And then you can also have different other stressing conditions, differential pressure especially, or the water concentration, the ionic contaminants in it. You can get some or the other and combine them. And then what you should not aim is in the AST is you destroy the stack or fail it in some way. It may happen, but you intentionally want to avoid that. So you should stay within what the manufacturer specifies in the range of operating conditions. You stay within the AST. So the conditions you select should still be within the allowable, permissible range of operating conditions. That is the aim, in order not to fail the stack itself. Yeah.
But maybe on the same point, when you say to compress from 8,000 hours, you 80,000 hours, you would take it down to how many hours of testing? Is it going to be 800 hours?
Yeah, that's the compression factor, and that is a choice to be made. It depends, of course, also on, because you have the rates as well, the power rates or the voltage rates, current rates. First of all, the stack should withstand it, should be able to follow that, as well as the test equipment you use to do it. So there's a certain limit as well in that. So you cannot compress it to a week everything. That will probably not, the test equipment will not be capable of doing it.
Just a quick question on this AST issue. The problem is that when you compress into time axis, information that you get is supposed to be used for prediction. And do you have any feedback related to the algorithm or the technique that can be used for extrapolation and prediction of what you get from short-term experiments and turn this into long-term prediction? Because this is probably written.
Yeah, I mean, there has to be a lot of data before you can make predictions. So it has to be a a set of a certain test campaign to be done in order to get to these predictions. So the first aim is to gather a lot of data and probably also to compare them to some ALT testing as well in order to find out how they work together. But as the development's going on, there will be probably more data, and the point is here that the data should be made open, so they should not be to get to the manufacturers itself. So it is benefiting the whole community. Is also when tests are done applying these protocols, the data are somehow made open in order to allow this at the end to calculate what stack life is. I know it's a difficult and tricky issue, and it's not always achievable, but that's a key point as well.
Thomas, there is a question in the chat. Two questions.
Yeah, so there are in the chat some questions. We see them. You see them, right?
Yeah.
Yes, this is I got the point. It was also in the past. So the aim, what we want to do in Europe is once we have done these protocols and also take the other procedures which have been developed in the past in order to do an exercise, a round-robin exercise. The JRC intends to have a PEM and AEM stack purchased by next year, and then to schedule a test campaign where the different testing procedures will be validated. And so this we want to do first in Europe, but there's no objection when some partners from the US wants to join in as well. So, but this is something to be discussed only next year. So the report actually aims at all three technologies, as at the beginning. I wanted to have feedback from the experts where we should specifically address the different technologies in it. So what I have now sent out for commenting is what the GRC thinks, what we have compiled together, and I welcome any feedback on specific aspects of the different technologies. Please write to me if you have some issues there and want to raise some points there. We can address that. Thanks.
I don't know if you can hear me.
Yes.
Yeah. Hey, this is Jeff Martin. Yeah. I think my question was not only about participation, but thinking from a global industry, research and business, if there are different activities going on to standardize on the same things, which then may end up with slightly different protocols or outcomes, that seems rather wasteful. So I think it was also about how can we actually align the activities and the outcomes to, I think it helps everybody globally if we arrive in a similar position. So it's the first question.
Yes. No, that's true. I don't know whether you have that refers to stacks, what you have now in the US developed. Or is it still a single cell level? Jeff?
Sorry, I actually didn't catch that. Could you repeat, please?
It is still in US development on single cell level or on stack level as well?
I think it's still at the smaller level of the cells.
Yeah, single cell level. Yeah. With this report we have done now here is basically we jump directly to stack level. The stack size is not defined, but we aim at ASDs for stacks. So that's probably the difference for the moment we have there.
But I think also, Thomas, that you have communicated the work we do in the EU to US counterparts in various events. I recall you traveling and presenting in the US, and maybe through the IEA Hydrogen TCP.
Yeah, so there is this question was raised already in the past, and it was on the participation as well as the round robin participation, as well as on the development of joint efforts. What I said for the other testing procedures we did was always that we first develop it in Europe here, and then we of course it's available. It will be freely available, accessible once published, and you can always come back to us with some feedback, and we could see how we can join them together to make a joint report, or whether we take it on to the level of the internationalization organizations to have it as input there, and with a new work life proposal, for example, and then to have a common approach there.
Right, and eventually, at the end of the day, the point is to use these testing protocols. We always make reference in our calls for proposals in relevant topics that the electrolyzer should also be tested using the JRC developed protocols. We haven't really seen this. Actually, the three anion exchange membrane electrolyzer projects were the ones that developed these testing protocols for this type of electrolyzers and shared with the JRC. And I don't quite recall if eventually you also did tests using those standard protocols. I think you did some tests with them, perhaps. Nino is shaking his.
But we are in principle aligned with the JRC proposal, and of course the passage through strong collaboration with them. The protocols developed into an ANIONE project were essentially coming from the PEM field, and initially, the JRC protocols were essentially addressing the PEM field, and of course this is really, of course, a lot of work that has been carried out in the last 2 years from JRC, starting from the PEM up and now including the AEMEL. Regarding the stressors, that was really an important, let's say, aspect addressed by JRC in the reports. We have essentially tried to align like recirculation rate, pH concentration, but in particular the temperature range. So, of course, depending on the type of technology, there could be some variation, but all these aspects were aligned. Also, regarding terminology, there was a first report on terminology from the JRC. And of course, that is another important aspect, because when we compare efficiency, electrical efficiency, or energy efficiency, or let's say light efficiency, we need to use a similar, not similar, the same formulas, because otherwise we cannot compare the results.
Yeah, maybe some for the dissemination. Now we have checked some publications, and there appears some reference here and there, and some papers to JRC developed procedures as well. Indeed, we were surprised by that, but we found sometimes we can have some papers where we are referred to people using the procedure tested within Europe as well as outside Europe.
Yeah, now it's becoming a standard, especially inside Europe. And what I would like to say is that I have attended recent conferences, and what I was surprised that some people, when I commented about the protocols, were using have commented that they don't know about the protocols, official protocols, and I said, have a look to the JC reports, because I think what we need to let's say, we need to promote these, let's say, reports or protocols in a conventional, let's say, electrochemical conferences, like TCS in US, ISE